Okay, my calculus geniuses, or calculus regularly intelligent people. The related rates. This is probably my most favorite thing to do, probably because I enjoy geometry as well as calculus, and there's actually a solution, I guess, to these things. It's not just a derivative. You're going to be doing like word problems, and word problems really happen in fake math, right? This is not real world problems. These are fake world problems, but they're math problems, and I don't know, they make sense to my brain. But we start off with a formula that you want to take the derivative of with respect to time. Okay, so this is where it's going to be different from what we've done before, is we're taking the derivative with respect to time, because things are happening at a certain rate, and rates happen with time, like miles per hour, or feet per second, or grams per minute, right? It's a function of time. Things are happening with time. So we're taking the derivative with respect to time. Okay, now notice you're never going to have time as one of your variables, right? Time is not going to be a variable. It's going to be the radius, or it's going to be a height, or it's going to be a hypotenuse, or it's going to be an angle, right? All of these things are not with respect to time. So anytime we take the derivative of, say, an x, maybe like 3x, okay, just like with implicit differentiation, we are always going to have an x prime, right? The derivative of 3x is just 3, but then we have this x prime business. Now, they're not going to call it x prime. They're going to call it dx dt, right, which are synonyms. These are synonymous, taking a derivative, a prime, and the dx dt notation. Those are interchangeable. Okay, as long as you remember that anything prime is a rate. Right? A derivative is finding the rate of change, aka the slope. So all these things are connected with the calculus. So let's see. Just remember, anytime you take a derivative, you're going to have a d whatever dt. dx dt, dr dt, d theta dt, dy dt, dh dt, dv dt, all kinds of volumes or derivatives with respect to time. So let's do some practice. Let's just practice taking derivatives with respect to time. Okay? So here we have the surface area of a sphere formula. How many variables do you see? Two of them. One of them is A. A is a variable, and the other one is R. R is a variable. So what does that mean about 4 pi? That's a constant, right? 4 pi is a constant. That's a number. Okay, just like if we had the derivative of 3x, what's the derivative of 3x? Is just 3. So what's the derivative of 4 pi r? Is 4 pi, right? Because the derivative of a variable is your constant. Yes, pi, there's lots of pi's in here because things are circular, and anytime we have a circular, we have a pi. Okay, so let's start on the left. dA, derivative of area with respect to time, is dA dt. Okay, so anytime we have a variable, you're going to take the derivative with respect to time. And if it's just a single variable with no number in front, then it's just a d, that variable, dt. Okay, so derivative of area, the rate of change of area with respect to time, equals. So now we have your constant, right? Because our variable is r squared. So let's take, what is the derivative of r squared? Right, 2r. So 4 pi times 2r. Okay? So let's simplify. Well, don't simplify that first. Let's just do it. 4 pi is your constant, so that stays here, times the derivative of r squared is 2r. But anytime we have a variable, we have to add in our Derivative with respect to time. Okay, so this one is how is the area changing with respect to time, and this one is how is the radius changing with respect to time, right? The rate of change of each of these things. So what can we multiply together? The 4 and the 2, right? 4 times 2, those are both numbers. 4 times 2 is 8, and then we have the pi, and then we have an r, and then we have our rate with respect to time. Okay, so there's always going to be this term, right? This is the new thing that we haven't had yet with derivatives. We're always going to have this derivative of our variable with respect to time. Okay, practice some more geometry. The volume of a sphere. Volume is 4/3 pi r cubed. And anytime you need a formula, except for maybe the area of a square, you're going to be given the formula in the problem. Okay, so you don't have to memorize all of your geometrical formulas again. So volume of a sphere. Let's do it from the left side. What's the derivative of V? dV dt. dV dt. Good. Derivative of volume with respect to time. Right? It's a single variable, so it just becomes dV dt. So now let's get into here. We're going to take the derivative of a constant times r cubed. Okay, so we're going to do the constant, right? The constant stays constant, so that's 4/3 of pi times. Now take the derivative of r cubed. What's the derivative of r cubed? 3r to the second power, right? 3r to the second power. And now we do our derivative with respect to time, which is dr over dt. Okay, so we do one thing at a time. We take the constant first, and then we take the derivative of r cubed second, right? So this is the derivative of r cubed, and then we multiply it by our rate with respect to time. Okay, so what can we simplify here? The 3 and the 3 can divide, right? 3 divided by 3 is 1. So we have a 3 in the numerator and a 3 in the denominator. So that leaves 4 pi radius squared times dr over dt. Okay? So taking the derivative with respect to time. Okay, let's look at our next one. Ooh, this is the Pythagorean theorem, Pythagoras' theorem. So we have 3 variables. So we're going to have 3 terms, which means we're going to have 3 dt's. Okay, so we'll start with our a term. The derivative of a squared is 2a. And then we multiply that by its rate with respect to time. So 2a times dA dt. Plus, now we move over to the b term. b squared. The derivative of b squared is 2b times the derivative with respect to time. Very good. And now we have our third one, our c variable. So the derivative of c squared is 2c, and then we multiply it by the derivative with respect to time. Okay, so all 3 of these things have a rate in them. All 3 sides. So if all 3 sides are changing, then we have all 3 different rates. All right, next we have this volume formula for a volume of a cylinder. Okay, a volume of a cylinder, where r is constant. Okay, so what are our variables in this equation if r is constant? V is a variable and H is a variable, right? So we're going to treat R as a constant, right? With a cylinder has a circular base and it has a circular top, right? So the thing that doesn't change is the radius. The radius is the same at the top as it is at the bottom, or it wouldn't be a cylinder. Okay, so radius is going to be constant. The radius of your cylinder is not going to change. So we're looking for things that are changing. So let's do this one. The derivative of v is dv dt. So there's no number, so it's just the derivative of volume with respect to time. Equals our constant, which is pi r squared, right? All those things are constants. The radius doesn't change. Times, what's the derivative of h? 1, right? So 1 dh dt. So the volume of your cylinder does not depend, or the rate does not depend on the radius, because the radius is constant. Okay, here's one that's a trig problem. Trigs are going to be probably the trickiest ones that we deal with. The trigs are the trickiest. Because in a trig problem, one thing is going to be constant, and one side is going to change. Right, so this one, it's telling us that 15 is the hypotenuse, is going to be a constant. So think about maybe a ladder leaning against a wall. Right, the length of the ladder doesn't change as the ladder moves. The ladder doesn't get smaller or bigger, but the distance away from the house does, right? So if we're pulling the base away. So here, our hypotenuse isn't changing, it's a constant. So what's our variable? The variable is theta, and our variable is x. Okay? So we take the derivative of cosine. What's the derivative of cosine? Negative sine of
Which one's the constant?
theta. So here's the tricky part. Times d theta dt, right? Theta is your variable. Sine is not your variable. That's your function. Theta is your variable. So we multiply negative sine times d theta dt. Now, how do you want to tackle x over 15? Right? What is constant and what is changing? The numerator is constant and the denominator is, switch that. The numerator is variable and the denominator is constant. So I'm going to rewrite this as 1 over 15 times x. Okay, are those the same thing? Is x over 15 the same as 1 over 15 times x? Yes, it is. So now I can see what my constant is. My constant is 1 over 15 times the derivative of x is 1 dx dt. And lastly, we have the area of a circle. We'll take the derivative of area, which is dA over dt, d capital A. Pi is your constant, times the derivative of r squared is 2r times dr dt. So 2 pi r dr dt. So every time we take the derivative with respect to time for any variable, you get a d whatever over dt. Okay, so that's the rate of change of your variable. So let's look at how these actually work in some problems. Okay, so let's read this and identify what we are talking, what are our variables and what are your constants. Air is leaking out of an inflated balloon in the shape of a sphere. So here we have a spherical shape at a rate of, so here's our keyword rate, at a rate of 230 cubic centimeters per minute. So what is changing for our balloon? Yes, cubic centimeters. So what's geometrical concept is written as a cubic centimeter? That is going to be our volume, right? The volume. So air is the amount of stuff inside of your balloon, right? That's the volume of the balloon. So when we know that the volume is it increasing or decreasing? Decreasing. So this is our rate of. Rate of means dV dt, right? That is our rate of change of volume. which in this case is going to be negative since it's leaking out. Okay, we are losing volume, which means our rate is negative. Losing volume. So we're identifying our variables. This is our rate of change of our volume. Okay? At the instant when the radius is 4, so that's a specific moment in time, find the rate of change of the radius. So how do we express the rate of change of our radius? That is dr dt. Okay, so look at all the variables. We have volume, right? Volume is a variable that's changing. We have radius is changing. Anything else involved in the volume of a balloon? I don't think so. Are any of these remaining constant? Right? No, none of our variables. Volume is changing and radius is changing. So we've done number 3. We've identified the rates. We know that our volume is negative 230 pi cubic centimeters per minute. We are trying to figure out what our rate of change of our radius is. Right, so that's what we are going to solve for in a second. Okay, so we basically did these 3 steps when we read our problem and we identified what's going on, okay, in our problem. So now number 4 is where you're probably going to be given the equation that we're going to use. Okay, so volume of a sphere was 4/3 pi r cubed. Right, that was the volume formula for a sphere from geometry. Now, step number 5. Here comes the calculus. Implicitly differentiate both sides with respect to time. So let's start with volume. The derivative of volume becomes dv dt equals, our constant is 4/3 pi, right? That's our constant, so we're going to leave that alone. And then we have our variable, which is r cubed. So we're going to differentiate r cubed, which is 3r squared times dr dt. We always have this derivative of the rate with respect to time. Excellent, y'all. That's the calculus. That is the calculus. So let's simplify this a little bit. Remember the 3 can divide out the 3 for a final simplified equation of 4 pi radius squared times dr dt. Okay, now let's plug in all the stuff we know. So we know the rate of change of volume. That's negative 230 pi. Right? That's the rate of change of volume. Air is leaking out of a balloon, so we are losing volume. So we have a negative rate of change of volume. Equals 4 pi. At the instant the radius is what? At the instant the radius is 4. So this is where we plug our radius of 4 into. Okay, and we have to square the radius. It's 4 pi r squared. And then we have dr dt, right? That is our variable. That's what we're trying to solve for, the rate of change of the radius. Okay, let's math this out. 4 squared is 16. 16 times this 4 is 64. So on the right side we have 64 pi dr dt. And on the left side we have negative 230 pi. So then to solve for dr dt, we divide both sides by 64 pi. So the pi's divide each other out. That's nice. So what is negative 230 divided by 64 reduced to? So our radius is changing at approximately negative 3.59. What are our units? Our units are centimeters. and it's centimeters per minute. So 3.59 centimeters per minute is the rate of change of your radius. So it's shrinking, right? The fact that it's negative means that our radius is getting smaller. Okay, a positive answer would mean that your radius is getting bigger, right? It's increasing if our volume is increasing. Okay, so that's how we do our related rates problems. Okay, let's try it again. Pretty nice. A stone is dropped into a calm body of water, causing ripples to form concentric circles. So we have the rate of radius, right? The radius is increasing at a rate of 1 foot per second. Okay, so we have the rate of change of the radius. So it says the instant, right? Exactly when radius equals 4, what is the rate of change of the area? Okay, rate of change of area. So we're looking for the area of a circle. So area equals pi r squared, right? That's the formula. Usually they're going to give you the formula if it's a volume or something crazy. But this one is a pretty basic geometric shape. So we have a pretty basic formula. Okay, so that's our formula, area equals pi r squared. Let's take the derivative with respect to time. Okay, so the derivative of area is dA dt, right? That's what we're trying to find, the rate of change of area. Equals our constant, which is pi, times the derivative of r squared is 2r times dr dt. Every variable gets a derivative with respect to time. So we know the radius is 4. When the radius is exactly 4 feet, the rate of change is, for our radius, what's our rate of change of radius? 1 foot per second. That's the radius of change, 1 foot per second. So let's multiply all of these things together. What's pi times 2 times 4 times 1? 8 pi. And what are our units for area? Square feet, right? Area is always a squared unit per second. Second is our time. So our area is changing at a rate of 8 pi square feet per second. Okay. Water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. Okay, so what is changing about the water? Right, so this is what variable? 3 feet. So this is your dV dt. We know the volume is changing. It's leaking out. So once again, it's negative 3 cubic feet per second. If the radius of our tank is 4 feet, at what rate is the depth of the water changing? So the depth of the water is your, right, slash height. So we're looking for dH dt. How is the height of our cylinder changing if we have a constant radius of 4? Okay, so remember our formula is volume equals pi r squared times h, where our radius is constant for a cylinder. Okay, so if our radius is constant, we can plug that number in here directly, right, with a radius of 4. So our volume is basically 16 pi times h. Okay, so if we have a constant from your problem, plug that in at the beginning of your formula so that we can simplify it down as much as possible to begin with. Because now we're going to take the derivative with respect to time. So for volume, that becomes dV dt. We have our constant of 16 pi, and the derivative of h is dH dt. So let's plug in our dV dt. We know that the rate of volume is leaking out at a rate of 3 cubic feet per second. So our one step is to divide both sides by 16 pi. So since that can't be simplified, that is a perfectly good answer, and our height is going to be feet per second is our rate of change of height, right? It's negative because the water is leaking out and the height of the water is getting shorter and shorter and shorter. So with related rates, we start with a formula, usually a geometric formula, almost always a geometric formula, okay? Plug in what we know to be true as constant, and then take the derivative of every variable with respect to time. Okay, and then plug in what we know and solve for what we're missing. Okay, with practice, you too can become good at these.